I'm happy to announce our last medal lecture, Union Medal Lecture for today, namely the Arthur Holmes Medal Lecture 2008, presented by Professor Anthony Watts and entitled Isostasy, Flexure and Geological Processes. Anthony, please.
Thank you very much, Mr. President, and for all of you staying this late in the evening to hear this talk. Next, please. I want to thank a number of collaborators who have joined me in this topic over the years. These are people I've worked very closely with and very much appreciate having that opportunity. Next, please. And finally, to my university in Oxford, the staff and the students there, for putting up with me and all the idiosyncrasies of doing this kind of work. Next, please. What I want to talk about is isostasy. It's a very old, more than 150-year-old concept in the earth sciences. And just to introduce the topic here is this illustration, one of my favorite illustrations of isostasy from Bowie, William Bowie's book, 1927, illustrating the idea that isostasy, that the crust is in some state of, it's buoyant, and it's in some state of equilibrium, in particular of flotation, on the underlying fluid mantle. He illustrated it in this diagram with a series of metals. And to me, as a practicing scientist today, I still find this concept amazing, that the crust that we stand on is in this state. And it's an intriguing idea and concept that actually is a very sort of fundamental one, I think, in the earth sciences. Next, please. I looked up Arthur Holmes, as I expect many of you in this room have a copy of Arthur Holmes's great book. And it turned out that Arthur Holmes was interested in isostasy, and he had a little chapter on it, which I think captures some of the ideas that isostasy is associated with processes, particularly geological processes, that actually may disturb this notion of a buoyant crust on a fluid mantle. For example, sediments may load the crust down and force this, what Arthur Holmes referred to as very slow flow of mantle seema from underneath where the region is loaded into an area that essentially is unloaded. And this unloading drives denudation, drives uplift, denudation, and erosion, which in turn supplies or supplies the sediments back into the basin. It's what he called one of geology's great cycles, the isostatic flow from loading of sediment through the mantle up into the crust and back again. He recognized that these processes actually disturb isostasy and that schemes of loading and unloading are important. Next, please. So what are the questions that perhaps Arthur Holmes may have enjoyed knowing the answers to? And I've summarized them here. What are the space and time scales of isostatic adjustment? It's very important to know over what scale this process actually works. The implications for understanding this, I think, are crucial for understanding how the Earth works and understanding what the Earth will do anyway when we are trying to unravel phenomena, for example, sea level change, the issue of rock uplift versus climate, and issues to do with mantle convection. We need to know what the crust is doing on its own, under its own mechanical systems, in order to isolate these factors. Next, please. I want to begin by how do we assess sort of globally isostasy? And still, one of the most traditional ways is looking at the gravity field of the Earth. And this field that you see here is an airy Heiskanen isostatic anomaly. It takes one of the isostatic models, an airy local model, and computes what the gravity field would look like if assuming this model of isostasy. This data set here is based on the very recent global Earth models. This one from the Eigen groups in Potsdam who have been constructing these fields. And it shows at once the broad areas that are in equilibrium, the ones with nearly zero anomalies, say between the greens and the yellows. Those areas are in a broad isostatic state of equilibrium. And the areas, the extremal areas, the white areas and the blue area, the deep blue areas, are areas that are very much out of isostatic equilibrium. And so the gravity field gives us this sort of spatial sense of where isostasy is operative and where perhaps it's not. Next. Another way of doing this is to look at the crustal structure of the Earth. And here I show a profile of the crustal structure through Vienna, actually between Vienna and New York. And the purple colored crustal structure is what we think the base of the crust, the crustal thickness, is on the basis of seismology. And the red dashed line here is the prediction from airy hypothesis. That's the local model of isostasy where elevated regions have deep roots. And you can see that in Europe, particularly in this piece of Europe that we cross here, airy isostasy does pretty well. It explains the depth of the Moho very, very closely. But there are many other areas, particularly the United States, North America, and Middle East, where we have large departures from the predictions of the airy model. And this is what makes it interesting. I think what you can see from these two diagrams combined is the general tendency of the Earth, and the Earth's crust in particular, through its buoyancy, to at least approach a state of isostatic equilibrium. The deviations you see are the cases where it's simply not approaching that state, at least not yet. Next, please. What I want to look at are some of the departures, and I've labeled up there on the left-hand side Hawaii. You can see a bit of blue and a bit of red, and we have large departures, essentially, in the isostatic models around Hawaii. Next, please. And the Dutch geophysicist Venning Meinitz in the 40s first looked at this departure in isostasy. He recognized that the gravity anomalies over the Hawaiian Islands here, very large gravity anomalies with flanking lows, were much larger than could be explained by Airy's isostatic model, which is shown in the green here. In other words, if we applied an assumed Airy isostasy, it wouldn't completely account for the high or the flanking lows. Venning Meinitz then developed a model which was more a regional model of isostasy. Instead of the crust going immediately down underneath a topographic load, it was actually deformed by less, but over a broad area. And he called this scheme a regional scheme of isostasy. And you can see with this blue line, this accounts pretty nicely for all the energy in the gravity anomaly. And he favored this model of regional isostasy over local schemes, such as Airy hypothesis here, to explain these departures. Next, please. And an adaptation, essentially an adaptation of the Venning Meinitz regional models of isostasy, again, that were developed during the war. These must have been sidelines, occupying scientists working late in the evenings in wartime America and Europe, just doing what they liked doing and thinking about isostasy. Because this is Ross Gunn, published this model, this elastic plate model, in the 1940s, separately as it occurred from Venning minutes. And it's a version of regional isostasy because we have a load on the Earth's crust. The crust will bend because it has intrinsic strength, and this is a reason why we may have regional rather than local model of isostasy, so that a given load, a geological load like a volcano, is supported by two things. One is the strength of the plate, and the other is the buoyancy of the foundation of the material underneath the plate, which, like in those local isostatic models, is assumed here to be a fluid, something with no viscosity that supports the load through its intrinsic buoyancy. And this model, a very simple model, explains quite a lot of the features of the crustal structure and the gravity anomalies around volcanoes. Next, please. And I'm going to show you just one example here from, again, the Hawaiian Ridge that Venning minutes studied all those years ago. Here is an image of the gravity field looking northwest across the Pacific Ocean, Hawaii here in the foreground. This range of what look like mountains are actually the gravity anomalies associated with the Emperor Seamounts in the northernmost part of the Pacific. And I think you can see on this map these lows around the big highs. These highs are over the volcanoes. Flanking the big highs are these lows. And flanking those lows are smaller highs. These are representing this bending down over large areas. And actually, there is a bending down under the big loads. And in flanking areas, there are bulges. These are predicted by this elastic plate flexure model. You can think of the bulges as being a consequence of the loads pushing down through that buoyant mantle. The material has to go somewhere, and it flows out from under the load and locally into bulges. The rest of the fabric here is fabric on the oceanic crust due to its creation at the mid-ocean ridge. But, for example, these fracture zones, but you can see some fracture zones go essentially through Hawaii, and you can see them come out the other side because Hawaii, the load of Hawaii is younger than the seafloor it sits on, and so it bends the crust down, and what we're seeing there is mechanics, the actual effects of the loading mechanics superimposed on the basic kinematic fabric, if you like, of the ocean floor. Next, please. And some years ago now, we ran a seismic line just off Oahu here in the Hawaiian Islands and imaged the top of the crust along that white profile there. Next, please. And it's a remarkable profile because essentially it verifies quite clearly Venning minutes' regional hypothesis. The crust, the red dots here are the top of the oceanic crust, and indeed you can see it's flexed downwards well before the volcano. This is the volcano on the left-hand side. There is a moat region here, which must be unfilled depression. It's filled with water, but it hasn't completely filled with material or products from the volcano itself. And we can take that very simple model, that simple elastic plate model, and calculate for a given load what the flexures or the deflection should be. And you can see that an elastic thickness, a plate with elastic thickness, meaning a certain strength of that plate of 25 kilometers, explains the shape of that observed deflection of the oceanic crust really well. And I emphasize this increase in depth of the oceanic crust. This is occurring 100 and nearly 200 kilometers away from where the load itself is being emplaced, meaning that the Earth's crust is reacting over at least those distances away from where we actually impose a weight on it. And it's quite a remarkable thing. And it becomes important in geology, which is dealing with regional scales of these sorts of numbers. Next, please. Next. And so if we want to study the deformation of the lithosphere, what are our options? Well, really, unfortunately, many processes in the geological record, for example, rifting, orogeny, are continuous processes. There is a continuum of process that is involved in formation of these features. And unfortunately, it's a fact of life. All that we have are what I've called here snapshots. We can see how the Earth, or the outer layers of the Earth, react under certain circumstances, certain limited ranges of time, ranges of distance, very limited patchwork, snapshots. We can't see the whole thing. And it's a limitation that we have to live with. But I'm going to show you some of these individual things we see and try in this talk and put them all together and see if we can make sense of how the lithosphere is actually behaving under loads such as volcanoes and other features. We've got essentially 4 types of snapshot here. We have the phenomena of coseismic deformation. This is deformation that occurs during an earthquake. It's extremely short. It may be quite large in amplitude, very short-term behavior. Essentially, the models that are used to model that behavior are elastic. In fact, the whole Earth, here shown in yellow pretty much, down to the core, is assumed to be an elastic half-space. So the short-term loads, coseismic deformation from 0 to, say, a few minutes that we see typically in earthquakes, is being modeled as elastic half-space. We go a little longer, and there's a phenomenon called post-seismic deformation. Many earthquakes show after the main coseismic rupture, the land in the vicinity continues to move. And it continues to move for days, months, years. And there is a phenomenon called post-seismic deformation. And this process usually models the lithosphere and the underlying asthenosphere as a viscoelastic material, meaning it has some elastic strength, but at some time or some condition, it becomes viscous. And this I've labeled in here as the transient regime. We've only got a snapshot. It's around this sort of shortish time following earthquakes. And the model is elastic plate on a viscoelastic half space. And it's that gives us the temporal variations of the deformation. Then we go a little longer, and we have ice, the reaction of the Earth's crust to the loading and the melting or unloading of ice sheets. We're now up to tens of thousands of years. And we have a phenomena called glacial isostatic rebound or glacial isostatic adjustment. The model here is invariably an elastic layer of some thickness, usually quite a large thickness, overlying a viscous mantle, something with a viscoelastic material, much like the case for the post-seismic deformation. Again, within the transient regime. And then finally, we have that example that I just showed you for the Hawaiian Islands. The use of that Flexure model with an elastic plate, but this time, elastic plate, but this time over an inviscid fluid, something with no viscosity. And we're dealing here with very long timescales, meaning essentially that the viscosity of the mantle below the crust is not important because the timescales are so long that it's essentially behaving like a fluid. So that's a very limited. Flexure is, again, like these other two, a limited snapshot of how the Earth is deforming. Next, please. Next. Okay. I'm going to show you 3 examples of each of these types of snapshots. This is from a paper by Nishimura and Thatcher showing the deformation associated with the 1959 Lake Hebgen earthquake in the Basin and Range province of the western United States. The key thing is look at this profile here away from where the earthquake occurred, and you can see large ground displacements. This is up to 300 millimeters in this period of time. Essentially, they re-leveled the road geodetically at various periods and have captured this movement of uplift of the order of 300 millimeters here over spatial scales of about 100 kilometers, following the loading of the crust by this earthquake. Next. And they've applied this model, which I've just mentioned, of the elastic plate over a viscoelastic half space, and put a fault in the plate, and essentially calculated the rebound patterns that you would expect for given thicknesses of the elastic plate and actually viscosities of the half space, and come up with the conclusion that they need, this is a root mean square plot representing viscosity on this axis, elastic layer thickness or strength on this axis, and finding that they need an elastic layer of about 38 plus or minus 8 kilometers to explain the shape of the ground deformation for this particular time duration that they see following this earthquake. So this phenomena, the post-seismic snapshot, timescales are decadal, the vertical displacements up to a few hundreds of millimeters, horizontal displacements a few hundred kilometers. Next. We move on to glacial isostatic rebound. This is a wonderful picture that Rhodes Fairbridge gave me many years ago of the black and white. I think it comes out nicer in black and white, of the lichen-covered raised beaches of the Richmond Gulf in central Canada. We would expect when the ice was loaded down on the crust, there would be a progressial lake of some sort. Any islands in this lake would have shorelines cut in them, and subsequently, if we could track those shorelines, then we could measure the inverted shape, if you like, of that proglacial lake, and from its shape, determine the elastic thickness structure of the lithosphere, in other words, its strength associated with that particular ice load. And this is indeed what Walcott did many years ago. This is the Algonquin. This is a 12,500 year beach level, and simply tracked distance from the edge of the ice sheet, plotted the data, and fitted the Flexure model, which I just discussed. And you can see from these numbers that it needs something between 70 and 100 kilometer elastic plate to explain the shape and geometry of that flexed or unloaded surface. So glacial isostatic adjustment is millennial in time scale. Its vertical displacements, you can see on this axis here, are in the hundreds of meters. And horizontal displacements, several hundreds of meters. In the case of Canada, much of Canada, nearly all of Canada, is presently rebounding from the last major load accumulation there. And we get quite large elastic plate thicknesses from this observation. And then to a third example of snapshot. This is the flexural model, the long-term model. And I give one of my favorite examples, which is the Amazon deep-sea fan system off the northeast Brazil coast here. You can see from the deflections of the bathymetric contours that there's a huge pileup of sedimentary mass here, just deflected northeast, presumably by the Brazil current, from the Amazon River, and we have a very large accumulation of sediments here. We can do the calculations, work out the size of the sediment load that is actually needed to fit the gravity anomaly. We've also determined seismically the thickness of the crust and thicknesses of the sediments in certain constrained areas. We can work out the elastic thickness associated with the bearing of the crust and mantle by this very large sediment load. And what we get is quite interesting. We get a result that the earliest sediments seem to have been put on a very thin elastic plate, or relatively thin elastic plate, maybe about 13 kilometers or so. But the Amazon fan, which developed during the Miocene, nearly 100 million years after this particular continental margin formed, was received by a much stronger lithosphere, a much thicker plate, something of the order of 35, 38 kilometers. So for some reason, the crust locally here had increased its strength with time, probably because the early sediments were formed on very young, probably hot and therefore weak lithosphere, whereas the Amazon fan itself, the mid-Miocene and younger Amazon fan, was deposited on much cooler and therefore maybe stronger elastic plate. So, timescales here, millions of years. The Amazon fan itself, we still have a delta forming off the Brazil coast as we speak. So we have sediments building a delta out on the shelf. They seem to have finished in the cone. There is a delta building out today, and it initiated about 10 million years ago. So millions of years, timescale. Vertical displacements, if you look at this shows the displacements from that dashed blue line there to the basement. It's several kilometers. It's 4 to 5 kilometers. So we're graduating up in scale on these deformations. And horizontal displacements, several hundred kilometers. Next, please. So with that result from the Amazon in mind, with a possible dependence on age, I'm going to show you two plots here that summarizes all the data that we currently have from principally ocean islands and volcanoes about how that elastic thickness of the crust, the elastic thickness that's describing the bending, how that varies with age of the lithosphere at the time it was loaded. And what we see is what you might expect intuitively, that we have low values when we have loads formed on very young lithosphere, low probably because the lithosphere there is very weak, mechanically weak, and gives small elastic plate thicknesses, and that as age increases, then when we put loads on, the structure appears much stronger, presumably as it cools and acquires a rigidity with time. I ring here the Hawaiian value. Remember, we said it was 25 kilometers elastic plate. Hawaii plots here because it's a young load on about 75 to 80 million year old seafloor. The plot on the right-hand side is simply elastic thickness on this axis against just the age of the lithosphere. This is to look at the possible effects of load time. Does it matter how long a load has been on the Earth's crust? Does it just sit there, or does it relax in any way? Does it try to adjust to that load? The data from the volcanoes is not certain, but it's suggestive, Hawaii here, it's suggestive that we have somewhat lower values for the young volcanoes here are in the reds and the oranges. Old volcanoes, old seamounts are in the blues. It suggests that the young ones have higher elastic plate thickness than the old ones, meaning that maybe we do have some kind of relaxation on those sorts of timescales. So putting the two things together, the fact that we have elastic plate thicknesses here, which, by the way, I forgot to mention, is substantially thicker than, say, what we normally think of as the seismic or the thermal thickness of the lithosphere. We have that phenomena where we increase with age, the strength increases with age, and then this phenomena, apparently, where the strength seems to be decreasing with time, the longer the seamount is on. Next, please. So we have some kind of stress relaxation from the very thick seismic thickness, which we can think of as a short-term mechanical thickness. The duration of the seismic waves is very short compared to the length of time it takes to form a volcano. And then a subsequent relaxation, maybe on the timescales of 1 to 2 to about 120 million years, where the system continues to adjust. Next. So there are two things. There's thermal cooling, which strengthens the lithosphere, and a load-induced stress relaxation, which weakens it. It seems from the ocean that the cooling wins. So we have, when we plot elastic thickness against age at the time of loading, that's the dependency we see is on the edge. And you can see it's a very good fit to these isotherms. Most of the data is between the 300 and 600 degree isotherm based on thermal models. Next. So we could take that model, and this is some work that Xixi Zhong and I did a few years ago now, and construct a model that will fit that phenomenon about how would a load react when you put it on the Earth's crust. The appearance, at least in the ocean lithosphere, is we put the load on. Initially, there's a very broad deflection, which is essentially elastic, and not by a large amount, but over a huge area. Then the load, with increase in time, the crust starts to relax. It actually weakens. It deepens. Here it is at 10,000 years, 100,000 years, 1 million years. It continues to go down. And then it sort of bottoms out. It reaches its, let's say, its steady state, flexural isostatic compensation. It's done. But in that process of deepening, the bulges that were once at the edge of the volcano move in towards the volcano. And we have bulge migration. The basin, the depression around the load is deepening, but it's also shrinking in spatial extent. A very interesting result. It's the first clue that we were convinced that we could say, well, this is maybe how it would react in time, because we only have these snapshots. Next. The implications are quite profound for a range of subjects. And I just want to mention, in the case of sedimentary basin formation, that if the basinal architecture is changing during the loading, in this case the sedimentary loading, it will have a profound effect on things like onlap patterns. Onlap at the edge, we might get onlap over a very wide area because the lithosphere is initially very strong and bears it over a wide area. And then as the stress relaxation kicks in, we would get patterns that stratigraphers and sedimentologists would call offlap. So we would get onlap early on and offlap later. If we didn't know otherwise, and if we were based, say, in Exxon research labs, and we saw these stratigraphic features, we might say, this is sea level rise, and this is sea level fall. Yet here, we've produced the observational patterns entirely through the mechanics of the system, the loading phenomenon. Next, please. And I just include this to point out the implications for facies in sedimentary basin architecture too. That if these bulges really are migrating inwards towards the loads, it's very easy to see how that they could control or contribute to facies variations. So if we have a bulge moving through the system, it means that, say, at a time 1, we had a section here that was essentially rather deep water. That region would then shallow, and then as time 3, when the bulge moves through, that same site would go into non-deposition. So we would create sedimentary facies from the bulge migration. Again, produced entirely from the tectonics, not the sediment flux, or not from sea level. Next. Okay, I just want to mention just an example from the continental lithosphere. I've spoken a lot about the ocean. And there's been some controversy about elastic plate thickness in the continents. It's more difficult to determine good numbers that everyone is happy with. But I just want to show you a case that, to me, is a clincher that says that the continental lithosphere has very high elastic thickness. And it's the case of the Ganges Basin in northern India. We can model here the observed Bouguer anomaly, the Bouguer anomaly being a nice reflector, if you like, reflecting the bending of the plate. It goes down where the plate is bent, and the shape of the Bouguer anomaly will give us the key elastic thickness constraints that we need. Basically, if we take the topography that's in the high and lesser and the higher Himalaya, and take the topography up to the Indus-Sangpo suture, which is the main suture that occurs within the Himalaya fold belt, separating Eurasian plate and Indian plate, if we take the loads up to that point and calculate the flexures, we get very nice fits here. This thick black line is for a 70-kilometer thick elastic plate, which means quite high values for the elastic thickness. And we can actually trade, if we're not sure about where the edge of the load is, we can vary that. But we still, if we do allow that to vary, we still find that we need thick elastic plates to explain the observation. Using a green line here, say having a thinner elastic plate, as thin as the crust itself, doesn't quite do it. It doesn't explain the wavelength, and it doesn't explain the amplitude of that bouquet anomaly. So I'm, if you like, in the school of relatively high, don't know quite how high, elastic thicknesses for continental lithosphere. Next. So with that in mind, we can take all the data of global elastic thickness data, make a map, and this is essentially a strength map of the lithosphere. The case we were just looking at, India, with the blues are high, the reds are low values, shown here by this circle. And it's quite an interesting map, and it's a regional, if you like, strength map on long time scales. Next, please. We can look in quite some detail. Here's a profile that connects the high elastic thickness in India, goes across Africa into South America, and look at its correlations. This is elastic thickness here. This is topography. So we have high elastic thickness in India and in South America. Look at its correlations with other physical properties. For example, heat flow and S-wave speed anomalies from seismic tomographic studies. The regions of high elastic thickness have low heat flow and fast S-wave speeds. Regions of low elastic thickness, for example here on the Red Sea Rift, we have high heat flow and slow elastic S-wave speeds. So we seem to be getting correlation between elastic thickness, rigidity, temperature, strength of the lithosphere. I'm looking at these correlations now in much more detail. Next, please. Next. So just repeating that the cratons, the shield areas, like northern India, very high elastic thickness. Rifts have much lower elastic thickness. Next, please. There's been a controversy which has been delicately termed creme brulee versus jelly sandwich. Controversy that has sort of originated in Europe, I think. It's been extended outside. And the question is, does that elastic thickness deal with this controversy in any way? Creme brulee is the notion about how the strength is distributed with depth. Is it all in the crust, as creme brulee model would imply? Is it the top bit that is the strong bit? Or is it mainly the mantle, the deep bit, that's the strong bit? The jelly sandwich recognizing that the crust, the upper part of the crust, is probably strong because it's cool and brittle and will respond to, has faulting, and we know it is associated with earthquakes. And elastic thickness parameters don't really help us a lot with the rheological model because we only get a single number of elastic plate thickness. And it's a reminder that this plate thickness is a sort of integrated strength. We don't actually know in detail where it's coming from in depth. But it is interesting that when we have strength mostly in the mantle, this is the only way that we can increase the elastic thicknesses and get numbers like 60, 70 or higher kilometers. So you can see that people who derive these high elastic plate thicknesses will tend to favor jelly sandwich. And jelly sandwich combined with strong mantle. And so we are, from the elastic thickness distributions and from the values, inferring things about the rheology of the lithosphere. Not an unsurprising result, perhaps. Next, please. And in terms of those earthquakes, we know we have a seismogenic layer in the upper part of the crust. In fact, this green shaded, this orange shaded region in each of these panels shows that. The lack of deep earthquakes. If you're creme brulee, you would say the mantle's too weak to generate the earthquakes. The jelly sandwich, the mantle actually is too strong to generate earthquakes. These are fundamental questions we don't, and I can't present to you the answer, that we need to know about. But elastic thickness has the potential to provide us. Next, please. So let me just, in the final moments, just wrap up to see if we can deal with a single model. I call it towards a model that links all these elastic layer thicknesses at the different time scale. Here's the ocean in blue, and this is simply the results from all these dots are ocean islands and seamounts, and they show our predicted change in elastic thickness with age on this diagram here. So it relaxes, the lithosphere appears because of the low viscosity underneath the lithosphere, relaxes very quickly, and then it flattens and acquires more a sort of approaches really the steady state long-term position. The oceans are plotting within here. Next, please. When we put on all that continental data, we complicate the issue greatly, as often happens in continental geology. But just notice all these gray areas here are from the earthquake loading story, the co-seismic deformations and the post-seismic deformations. They're short time scales. They tend to give thicker plates. Not always, but they tend to give thicker plates. And elastic thicknesses from the continents have highish values, and of course these are associated with much older loads. We don't have precise control on the ages of these loads, but it could well be into it could be giga years or 2 giga-year ages for some of these elastic thicknesses. So what it appears when we look at values from the same continent, for example, here's Lake Hebgen, that result in western United States, giving a plate thickness 38 kilometers or so. Here is another value from the associated with the Lake Bonneville, the unloading of the water from the former Pleistocene lake of Lake Bonneville raised the shorelines, and we have an elastic thickness determination, longer time scale, from Lake Bonneville. And that's actually less than the 38. It's about 25 kilometers or so. And then finally, we have elastic thickness estimates from the East Coast United States, from loads, from orogenic loads and fallen basins, which are even lower still. So it looks within the same continent that we may be seeing a path, one of these paths that we seem to see much better in the oceans, of relaxation associated with something that starts with a lower viscosity overall than the ocean and then relaxes. So a summary, next please, of what all this is showing us is that we have some regions, for example, the plate boundary, as we approach the plate boundary regions of the western United States, where we have a lowish viscosity underneath the lithosphere, and then a quick relaxation, and then we approach some kind of steady state up here. We may have other areas, for example, where we have those very high elastic thicknesses on very old cratons, where we have lower viscosities below the lithosphere, and then we approach a steady state, this point here, and then it flattens. So we have regional variations in elastic thickness, viscosity of the uppermost mantle, and this is giving us this different appearance of how loads are adjusting on the Earth. So not only have we got a time scale and a spatial scale issue to look at, it actually matters where the load is. They're simply going to relax much quicker in the basin and range region than they are in the eastern United States. And this is the data that is suggestive of that. So we're learning in increments about what is happening under load. Next, please. Next. Just repeating. I just want to look very briefly. Two implications of this early relaxation. If we're in a region, say near a plate boundary, then it may be that this flexural elastic plate thickness applies to quite a wide range of loading phenomena. And here is an example in the Andes where we take the loads of the Andean mountains, put them on an elastic thickness structure that was actually determined from modeling the gravity field, predict where the flexural bulges are and where the flexural depressions are, and then look at the relationships of those bulges and depressions to the drainage patterns. We can see some river systems, say in the bend region of the Andes, that come out, exit the mountain belt. They sort of see or feel the flexural bulge, if you like, and then deflect and go northwards in this case, avoiding the bulge. In other regions of the mountain belt, we have enough sediment flux that we've actually infilled a large part of the flexural fallen basin here in such a way the rivers are now able to get across and over the flexural bulge. Next, please. And essentially off here, the river exiting here, Pilcomayo system here, has generated a huge megafan of sediments. And the megafan has filled the flexural fallen basin and allowed river systems to go straight across the bulge and join the trunk stream, the Paraguay River, this massive river system in eastern central South America. So we see we can compute, take these elastic thickness variations, compute the bulges, and actually it impacts the drainage patterns. Next. On the long time scales, in the same region, we have evidence for long strike changes in the structural styles of the mountain belt. Essentially, around the bend, we have thick skin tectonics, in the bend, thin skin tectonics, and thick skin to the south. We can actually explain this with that previous elastic thickness structure map, which showed very high elastic thickness in the bend region. Next, please. And here is a contour from that previous map. Everything above this side of the contour is very high elastic thickness, maybe 70 kilometers or higher. We can explain the structural styles by simply taking into account that if we had high elastic thickness, we would have shallow décollement, shallow surface on which fold and thrusts could develop that comprise the fold and thrust belt. And this would mean that we could generate perhaps rows and rows of these valleys and ridges, and it would be easy to do in a shortening system. If the elastic thickness is too low, on the other hand, say to the north and to the south, then we would have more basement involvement. We'd have a steeper décollement, more basement-involved rocks, and we would have narrow fallings, and influencing the structural styles and indeed the landscape shape and the landscape amplitudes simply from the inherited elastic plate thicknesses. Next, please. Here's an example. I mentioned mantle convection and parameterizing the elastic plate thickness of the lithosphere is a useful thing to do. And in the ocean, we can demonstrate on this diagram, I won't go into the details of the diagram, we can quantify the contribution that we would expect to the gravity field of lithospheric flexure, for example, this isostatic flexural balance. And what we see is that it tapers off, the models taper off at wavelengths about 1,000 to 2,000 kilometers. This means at those wavelengths higher than that in the gravitational field, we will not see isostasy of any form. It's simply too long a spatial scale. It's very interesting that actually the data show that we have some features here at the long wavelengths. And really, the only argument is we've taken, in a sense, the lithosphere out. These must be expressions of sublithospheric mantle. Perhaps some form of density-driven convection. So very interesting as we try and document this spatially, say, over big ocean basins. Next, and this is really the final slide, some conclusions. Next, please. If we quote perhaps Watson, the turn of the century, what would Holmes have thought about this? Of course, we don't know the answer. Next, please. But Holmes realized the connections between isostasy, the natural, if you like, movements of the Earth's crust and upper mantle, underloading, and its links to things like landscape evolution, mantle convection, some of the things I've been mentioning here. Today, I think this issue is even more important. We definitely need to quantify better what the lithosphere is doing. Indeed, what the Earth is doing anyway. What are the natural rhythms, of which isostasy is simply one of them? What are the natural rhythms of the Earth systems? Because, in my opinion, we need to get these right, quantify these right, if we're going to try and isolate things like sea level change, climate change in the future. Thank you very much.
Thank you very much, Anthony, for sharing with us your snapshots in space and time. This was the last of the 3 Union Medal lectures in 2008, and I would like to thank you for your attention and enjoy the evening. Thanks a lot and bye-bye. And again, an applause for all our medalists.